Hello students, in this video we will study about the effect of temperature on resistance and how resistance depends on the temperature. Okay, let's we understand by the diagram. Let this is the conductor of length L and the cross sectional area A. And when potential difference V is applied across the ends of the conductor, because this end is connected to the positive terminal, that's why here positive potential will be developed, and this here negative potential will be developed because this is connected to the negative terminal of the battery. Here potential difference is there between two ends. Due to the potential difference here, electric field will be produced, that is vector E. So the direction of electric field will be positive to negative phase. Okay, actually electric field is the electrostatic force on the free electrons. Okay, due to this electrostatic force, electrons will be attracted towards the positive phase along this direction. Okay, along this direction. Now let this is electron moving along this direction and it will collide with this atom. After collision, it will change their paths and move along this direction. Here another atom is there, that's why it will collide with this atom. These are the two successive collision, and the time taken between two successive collision is called the relaxation time. Now if temperature is increased of the conductor, then the relaxation time will decrease, and the relation between relaxation time and resistance is directly inversely proportional to the relaxation time. When tau is decreased, R will increase, means resistance increases. Here it means when temperature is increased, the resistance of the conductor is also increased. Okay, now what is the relation between the resistance and the temperature? Okay, so we will find this. Now let at 0 degree Celsius let the temperature of this conductor is T0 or T0 at 0 degree Celsius. At this temperature, resistance of this conductor is R0. Okay, when temperature is increased up to T degree Celsius, at T degree Celsius, the resistance of the conductor is R. Okay, so here resistance of the conductor increases. So resistance of conductor, the change in the resistance or the how the resistance increases. So the difference of the resistance in different temperature R0. This is the change in the resistance of the conductor. Okay, or this is the value increased. Okay, now this change or this increasing resistance of the conductor is directly proportional to the initial resistance R0. This is the initial resistance, and this change in resistance is also directly proportional to the change in temperature, del T. Del T is equal T minus T0. This is the change in temperature. On combining both, this is first, this is second. Here R minus R0 directly proportional to R0 into del T. Okay, or R minus R0 equal, here proportionality constant, let the proportionality constant is here alpha, and R0 del T. this alpha is the proportionality constant, and here this alpha is called the temperature coefficient of the conductor. Temperature coefficient of the conductor. Okay. Now, here from this equation, this is the third equation. From third equation, here R minus R naught equal alpha R naught del T, or R equal R naught plus alpha R naught del T. Okay, R naught is common, so R will be equal with we can take common R naught 1 plus alpha and alpha del T. This is another equation, fourth equation. This is the equation for final resistance when temperature is increased. Okay, so let this equation is fourth equation. From this equation, R naught is constant at 0 degree temperature for this material, the material of this conductor, it will constant, and alpha is also constant, that is the temperature coefficient. So these are constant, that's why R will be directly proportional to T. Means, what is the relation between the resistance and the temperature? Here means when temperature is increased, resistance is also linearly increased. Okay, so this is the relation between temperature and the resistance. From the equation third, here we can find the value of temperature coefficient. So from equation third, temperature coefficient alpha will be equal R minus R naught into R naught upon R naught into del T, but del T equal T minus T naught. Therefore alpha will be equal R minus R naught upon R naught into T minus T naught. This is the expression for the temperature coefficient of the conductor. Okay, we can find the temperature coefficient for every conductor or insulator or semiconductors. Okay, this is the formula of the final resistance, and this is the formula for the temperature coefficient. Okay, now we will discuss about the example related this formula. In this question, VI graph for a metallic wire at two different temperature T1 and T2 is shown in figure. Which of the two temperature is higher and why? This T1 is the temperature for this line and T2 is the temperature for this line. Okay, there are two temperatures. Okay, now which temperature is more, T2 or T1? Okay, so take a point at this line for temperature T2, draw the normal on the voltage axis or potential axis. Let this is the value of V2 for temperature T2, and on the I axis draw again a normal. Let this is the current corresponding value of V2. So let this is I. Okay, take a point on this line, okay, and draw the normal on the V axis from this point. Let this value is V1 for temperature T1. You know, at constant current, here potential are different for T1 and T2. Okay, this potential is less, V1 is less than V2 potential. Okay, now we have to find here the slope of these lines. The slope of this line for T2 T1 temperature, slope for T1 temperature, slope equal, what is the slope? Slope is change in the y-axis upon change in the x-axis. Here in x-axis, here potential is taken, and here in the y-axis, here current is taken. So the slope in y-axis, this is the current I upon, for T1 corresponding value of V is V1. So here V1. This is the slope for T1 temperature. Okay, but we know that resistance R1 for T1 temperature is equal potential upon current. So for this temperature, potential is V1, but current is common for both. That's why here I will be there. Okay, so it is clear from this equation and this that the slope is inversely proportional to the resistance. So the resistance of the conductor for T1 temperature will be equal to the reciprocal of the slope. Let slope is rho. So this is rho 1. So it will rho 1. Okay, now, and the slope for temperature T2, slope for temperature T2 will be 2 equal I upon V2. Value or change in y-axis means this is change I, and change in x-axis V2 minus 0 equal V2, and here I minus 0 equal I. So this is the slope. Okay, but the resistance will be R2 equal V2 upon I. This is the formula by Ohm's law, and this is also the formula by Ohm's law. From this equation and this equation, it is clear that the resistance is reciprocal to the slope. Okay, now you know from this diagram V1 is less than V2. Since V1 is less than V2, okay, here in this from this this equation and this equation, okay, here V1 is less than V2, but I is common for both, and V1 is less than V2, so V2 is reciprocal to the rho, or rho is the reciprocal to the V2. When V2 is greater, then the value of rho will be decreased. Okay, means for this condition, rho 2 will decrease. It is less than V2, that's why it will increase, and because this is greater, that's why it will decrease. So rho 2 will less than rho 1. Means these are the slopes. So the slope for T1 is greater. This is the slope. It is clear for this from this diagram. Slope is higher, slope is less. Okay. So the slope of for T1 is greater and slope for T2 is smaller. So from this equation and this equation, because rho 2 is less, this is 2 R2, because rho 2 is less than rho 1, so R2 will, this is less means R2 will greater than R1. Therefore R2, this is smaller, that's why it will increase. So R2 is greater than R1. Understand?